In this fifth video for AP Chemistry at Allen High School, we're going to be working 3 examples that each have a slight variation on moving on and off the mole road. So let's jump in and get started. We have the Haber process. Those of you who are in IBHL 1, you want to make sure you pay close attention to this. It's an expectation that you are familiar with this reaction. And we're making hydrogen plus nitrogen to make ammonia. Now we want to balance that equation. That's where we're going to get our mole ratio. We need a 2 there and a 3 here, and we have a balanced equation. Now the question says how many liters, and notice it says those wonderful little words or acronyms STP. It's ammonia gas, and we want to know how many liters at STP. If we started with 52.88 grams of our hydrogen, notice I put it directly underneath the hydrogen, and it says that we have excess nitrogen available, which means that in terms of our mathematics, we don't need to worry about the nitrogen anymore. Certainly in terms of the reaction it's needed, but not in terms of the mathematics. So we need to get up to the mole road. Mass to moles, use molar mass. And then we can drive down the mole road to moles of ammonia. That's the only way we can relate one substance to another. In other words, there's no shortcut down the alley. You have to go down the mole road on this. And then we have moles to liters. Now, since it's moles to liters and it's STP and it's a gas, I can use that conversion factor. 22.4 liters is equal to 1 mole. You have to be careful how you use that, but in this case, we can use that. It'll simplify our work. And so I've got to go mass to moles using molar mass. Then I need to go moles to moles, and then moles to liters. So I have a 3-step problem here. So I have 52.88 grams. Notice that it's hydrogen. Don't forget about your diatomics. However you memorize them, either from the periodic table or some phrase like I bring clay for our new house. There's a number of ways. Other people say Brinkelhoff. So whatever you want to do, don't forget about those diatomics. So when we're dealing with pure hydrogen gas, not hydrogen bonded to anything else, only when it's pure is it diatomic. 1 mole is going to be 2.02 grams. Now I want to get rid of moles of hydrogen, and I want moles of ammonia. So I'm working on this step here. If you set it up so that your units cancel, so I've got moles of hydrogen in the numerator, moles in the denominator, look up at your balancing. There's a 2 in front of the ammonia. There's a 3 in front of the hydrogen. And so that's how I set that up. Or you can make sure you remember that it's always where you're going to over where you're coming from. Now I have that one last step to do. I want to eliminate moles of ammonia, and I want liters, and since it's a gas and since the conditions are standard temperature and pressure, I can use this very simple conversion factor. Now if it was a gas and it wasn't STP, you'll see in a little bit that we'll use Pevner. And you could have used the ideal gas law for this as well. It just is not necessary. Now, if we worked this problem, we have 4 sig figs in our original, and it was all multiplication and division. I'm going to take that as 195.5 liters of ammonia. Now remember, that would be our maximum or our theoretical yield. In this case, maximum or theoretical yield. Now let's take a look at a solution reaction. We just started working on our double replacements. This is a neutralization, which is a subset or a special type of double replacement. I have barium hydroxide. I have sulfuric acid. Remember, ic comes from the polyatomic 8, which is sulfate SO4, and it's going to form a salt. So the barium is going to go with the sulfate so that the positive goes with the new negative. And hopefully you're slowly but surely memorizing your solubility rules. That would be a solid. And then I'm going to make two waters as the H plus of the acid goes with the OH minus of the base. So that's my balanced equation. Let's write down what has been given here. I have 24.3 milliliters of a solution that's 0.33 molar. Now, you might want to write that as 0.33 moles equivalent to every 1 liter that is delivered. So we can use now molarity as a conversion factor. We want to first get up to the mole road. So we're going to go up to the mole road. This time we're going to use the molarity to go to the mole road. Now the question was, in this case, what volume of our acid would be required to fully neutralize it if we had 0.48 molar, or again, we may want to use this 0.48 moles equal to 1 liter. So if you're going to calculate molarity, you really have to hop out and plug into the formula. But if you're going to use molarity, if it's given, you can typically use it as a conversion factor in a dimensional analysis. So then I've got to go moles to moles, and then moles to volume again using that molarity. So remember, your key is always to find a way up to that mole road, because that's how we can compare these two. Now you'll notice in this case that I have a 1-to-1 mole ratio. You still have to show that mole ratio in the problem in order to get full credit for work. If you mess up, you've lost a point automatically for not showing that. So I have 24.3 milliliters. Well, I can't go directly from moles, but if I go milliliters to liters, then I can use my liters to get to moles. So I'm first going to convert my milliliters to liters. If you're pretty sure of your direction on your decimal place, I do not require you to show this for me at this level, but that would be our conversion from milliliters to liters. Now, notice what I do. I want to get rid of liters of the barium hydroxide solution, and I want moles of just the barium hydroxide. Well, the molarity tells me that for every 1 liter of the barium hydroxide solution that I deliver into my reaction vessel, I will get 0.33 moles of barium hydroxide into the reaction mixture itself. Now we have our mole to mole ratio. We're at the mole level. If we stopped our calculation, we'd be right there on our map. This time we want to now move down the mole road. I want to eliminate moles of barium sulfate. I want moles of sulfuric acid. Now, if you got this right and it's shown clearly in the equation that you've balanced it, you probably wouldn't lose points. But if, on the other hand, your answer was wrong, say you popped it into your calculator incorrectly, which, you know, we do all the time. I do it too. Anybody can do that. Then I go hunting for partial credit. And if I don't see that mole to mole ratio explicitly in the problem, I can't give you that partial credit. Now, I want to get rid of moles, and I want to go to volume. It didn't tell me that I had to go back to milliliters, so I'm just going to go to liters. So for every 1 liter of solution, I have 0.48 moles of sulfuric acid. And if you perform that calculation, what we are going to get is 0.017 liters or 17 milliliters. And we might do this in a titration with a burette or something similar to that. All right. Now, we have one more to do, and it's already 10 minutes into this video, so I'm going to hold off on that till the next video. But I want to go ahead and give you the answer so that you can try it yourself. And, you know, if you can do it yourself, you won't need my help, and you'll know that much more how much you know of your objectives, which one of your objectives you know. So the answer I got for number 10 was this. So if you are going to give that a shot, check out your answer. If you get the right answer, you don't even have to watch the video. So good luck.